Hello, and welcome to this video on spot size in laser welding. You will find this video on the laser welding playlist in this YouTube channel named the Weld Nugget. To begin with, let me start by sharing the screen so you can follow along with the PowerPoint that I'm going to use for discussion. My name is Girish Kelkar, and I am a welding consultant operating as WJM Technologies. Additional information about my consulting and training business is on the web at welding-consultant.com. Today, we're going to review the topic of spot size in laser welding. If you're new to this subject of laser welding, I would recommend that you review the other videos in the playlist as well, such as laser welding fundamentals, different types of lasers, laser beam quality, and pulse shaping in laser welding. First and foremost, we're going to look at how or why do we use lasers. So what is so unique about laser light that we need that for materials processing? Laser light is special because laser light is monochromatic. Monochromatic means a single wavelength. And collimated. Collimated, that means the beam of light is parallel. Combination of those two factors results in the light being focused down to a very, very small spot size where enough photons can be collected in a small location where you have enough energy density to initiate melting. If you take an ordinary light, even a high power light bulbs like those in the sports stadiums used at night, the power is very high, but there are many wavelengths in that light, and the light coming out of those sources is not parallel. So it is very difficult to focus it down to a small spot size. And now we're going to look at how do we actually calculate that spot size. On the next slide, we see an equation which can be used for a collimated beam. That means assuming the beam is already parallel, we can calculate the diameter of that spot as shown over here schematically. That is the smallest diameter that the beam will narrow down to coming out of the focus lens, is a function of the wavelength, lambda, focal length of the lens, m square. M square is a measure of beam quality, and you can review that information in the previous playlist on beam quality. And d is the diameter of the beam. Now, this is not the lens diameter. This is the diameter of the beam. Of these parameters, the wavelength and the focal length are well known, but the other parameters such as m square, the beam quality, is not easy to estimate. D, the lens, the beam diameter is also not easy to estimate correctly. And we don't always know exactly if the beam is collimated. So that is why, even though this equation is possible to be used, it's not very practical. In reality, a lot of the lasers that are used now for welding, the energy comes to the focus head through a fiber. So here I'm showing you a schematic layout of a focus head where the fiber is coming into the focus head. Now, this fiber can be the feed fiber or a process fiber. Feed fiber is the one where the laser light is actually generated in a fiber laser. Process fiber is a fiber that just transmits the laser light. So when I click the button over here, you're going to see the laser light come out. One of the interesting properties of laser light is when the light comes out from a solid medium to the gas medium, it starts diverging. So even though the beam is reasonably straight, it is still diverging. So what you have to do first is we have to make it parallel again by putting it through a collimating lens. Then the parallel beam goes to the focus lens, and then it focuses down to a spot size. So when I click the button, you will see the beam come out over here and go into the focus lens, and then focus it down to a spot size. The core diameter of the fiber typically can range from 15 microns all the way to 600 microns, but although in general, it is more usually in the range of 50 to 200 microns. So that is the typical size of the fiber diameter. The equation that we use to calculate the spot diameter is spot diameter equal to the core diameter over here multiplied by the focal length of the focus lens and divided by the focal length of the collimating lens. If the collimating lens and focus length are similar, let's say both of them are 200 millimeter focal length, and that's quite reasonable. They are usually fairly close. These two numbers will cancel out, and you will see that the spot diameter is exactly the same as the core diameter. So one of the important aspects of welding is to make sure that you have a reasonable spot size. It doesn't have to be too small. It doesn't have to be too big. If it's too small, then the energy density will be too much, and you might end up drilling on the part. If it is too big, you may not be able to make a weld. The spot size is also determined by how deep you want to go, how wide you want to go, what kind of weld it is. So there are many factors which go into selecting the spot size. So the first thing we need to do is determine what is the optical spot size that you would like. So if you have a certain layout of this focus head, and let's say your spot diameter is say 100 microns, and now you have a process or a project where you want a larger spot size. Instead of 100, you want say 200. So what you can do is change the focus length. You can go, if the focus length right now has a focal length of 100 millimeters, you can go to a focus length of 200 millimeters. That will double the spot size. Or you can change the fiber. You can buy a fiber which has a larger fiber diameter, core fiber diameter, and that will also produce the same effect. So you can either increase the core diameter or the focal length of the focus lens. Usually we don't change the collimating lens as much. So these are the two that we have the flexibility often to change the spot size. You can also try to go smaller or bigger. So that's up to you. So those are the choices you have in selecting the optical spot size. One thing you have to keep in mind that this discussion is purely right now about the optical spot size. The actual spot size, the welding spot size, can be different. So here I'm showing you a cross section of a spot, laser spot made on a piece of stainless steel, and it has been sectioned, polished, and etched, and you can see that the weld spot size is about 700 micron, even though the optical spot size is only 300 micron. So the optical spot size is a calculated number that doesn't change as long as you don't change the optics. But the welding spot size can depend on the welding parameters as well as the metallurgy. So for example, if you're doing pulsed welding and you have a longer duration pulse, instead of a 2 millisecond pulse, you decide to send in a 4 millisecond pulse, that will increase the spot size. Also, the metallurgy affects the spot size. So for example, stainless steel will usually produce a larger spot size as measured on the surface of the weld. Now, we're not talking about the penetration. We are not talking of the depth. We are only talking about the diameter of the spot as measured on the surface. If you use the exact same energy and the same optics and the same pulse on a piece of steel, it will have a larger spot diameter on the surface compared to aluminum. So before you go ahead and start welding, one of the first things you need to know is what exactly is the spot size, the optical spot size, and will it create the right weld spot size that will satisfy the requirements of the weld you're trying to make. So this is just one of the parameters that you need to understand. There are many others, and you can review the other videos to understand those as well. Okay. Thank you for your time. If you're interested in learning about welding and joining, please subscribe to this YouTube channel called the Weld Nugget. And there are quite a few other playlists as well on this channel, such as for resistance welding, metallurgy, and arc welding. And feel free to review those for your information. And wishing you the very best in your experiments with laser welding. Thank you.